here I am going to solve a problem in order to calculate the rate of flow inside any tube QV equals to A times V. Okay, you know A times V. A is the cross-sectional area of the tube, and V is the velocity of the fluid inside the tube. To calculate A is easy, but V, we must have a method, a certain configuration to find the velocity of the fluid inside the tube. One of the method is this configuration, where we have a conic tube like this, and we have here I connect this tube with a U tube like this one. You know, in general, inside this U tube, initially, we have a mercury. You know, we have a same level at each side. You know, here we have P0 and here we have P0. If we connect this one to the main tube, and inside we have a flow of oil or fuel or water, you know, here we have a large section. When we have a large section, S is large. In this case, we have a small velocity. If we have a small velocity, we give a large pressure at this point, And here we have a small section. So we have high velocity, large velocity, and we give a small p at this point. So the pressure here down is larger than the pressure here. In this case, the mercury inside will have a difference between each level. We have a height h between this point and this point. What is the objective here? I need to find the velocity and the rate of flow inside the tube by calculating the height between the height h. So in general, we have to find Q in function of h. For each value of h, we can calculate the value of Q. Okay? Here we can take this configuration, or we can take this configuration, or we can have another configuration to find Q value inside. For example, we can have something like this. We can put something like this. And we can put here one tube, and here also we can have one tube. It's open here. Okay, the same configuration. Here we have large section. So S, we can say here S is large. So the velocity is small, and P will be large. Here we have a small s, so the velocity is high. We get a small p. Okay, so P at this side is higher than P here. We can have the level here of the mercury or of the fluid will be higher than the level here. We can find Q value inside in function of the difference of height between this point and this point. Anyway, we have many methods to find Q in function of H. The objective here to find Q and by measuring the value of H. Okay, now let me solve this problem. Here we have simply oil is accelerated through a converging cone-shaped nozzle. Nozzle, I mean we have two sections. We have S1 and S2, as you see in the figure. And the nozzle is equipped with a U-shaped pressure gauge which contains mercury. Here we have this shape of U-tube, and inside we have mercury. Now, just I want to study the nozzle. First of all, the first point, I want to study the nozzle. And as I said before, I have to find finally a relation between Q and function of H. Let me add one point. If we have same section of the tube like this one, so in the U-tube here, we get the same level. You get here the same level because we have the same section. Here we have S. We get the same velocity and the same P. Here we have same S, same V, same P. You know, in general, we have A1, or by the continuity equation, we have S1 V1 equals to S2 V2. If S1 equals to S2, so V1 equals to V2. If you write Bernoulli equation, we have P1 plus rho G H1 plus rho divided by 2 V1 square equals to P2 plus rho G H1 plus rho divided by 2 V2 square. In this case, we have the same height here, H1 equals to H2. As you see, we take a point here and a point here. We have the same height here and here. We can eliminate H1 and H1, and we have the same velocity. In this case, we have the same pressure at the point 1 and the point 2. As we have the same P, we get here the same P applied on the mercury. In the tube, we get the same level. So we cannot have H between this point and this point. In this case, we need to have a difference in cross-sectional area of the tube in order to have a difference of P at the point 1 and the point 2. If P1 is not equal to P2, then we have a H in the mercury level. Okay, so now we come back to the problem. I want to study the nozzle. We have a volume flow. So here I give you QV. We can say QV is given, which is equal to 0.4 L per second. The oil crosses the section S1, I mean at V1, has diameter D1 equals to 10 millimeter. We have D1 equals to 10 mm. And we have a velocity v1 and p1. You know, I am calculating at the point 1. We have v1 and we have p1. Okay. At S2, you know, you have a flow of water out of the nozzle. At this point, as this point is open to outside, we have at this point P0. I am talking at this point. We have P0. We can say here P2 equals to PO equals to 10.5 Pascal. Okay, we suppose that the fluid is perfect. What I mean by perfect, it means we neglect the coefficient of viscosity. We don't take into account the viscosity of the oil. Here we have oil. L'huile, I mean oil. Okay. The second point, the nozzle is kept horizontally. What I mean by horizontally, it means we have the same height of the point 1 and the point 2. Okay, if I put like this the nozzle or the tube, so we have the same height for this point and for this point. Because in general, we have to take this level to find the height of this point and this point. We have the same h. So h1 equals to h2. And finally, we give the density of the oil equals to 800 kilogram per meter cube. Let's go. Okay, first of all, I want to calculate the flow velocity V1. I want to find V1. Okay. To find V1, you can use directly. You have QV, which is equal to 0.4. You have L. You have to calculate it in function of meter. Okay. You know 1L, 1 liter equals to 10 power minus 3 m cube. Or we can say 1 m cube equals to 1000 L. Okay, so we can write here directly times 10 minus 3 m cube per second. You know Q is a volume per second. You know Q equals to A times V. You can take any point inside the tube. Here, be careful. In the nozzle, we have dynamic fluid. In the U-tube, we have hydrostatic fluid. You know, in the case of dynamic, you can use directly Bernoulli equation and the continuity equation. In the case of U-tube, we have to use, you have to take 2 points at the same level, and we can use P2 minus P1 equals to rho GH. Okay, now we are studying only the nozzle, so we have to apply Bernoulli equation and the continuity equation. Here we have Q equals to A times V. You know, I think I want to calculate V. V equals to QV divided by A equals to 0.4 times 10 power minus 3 divided by A. A, you can take this one or this one. Okay, now I want to calculate, V1. So we have to use A1 or S1. You can write A1 or S1. you know S equals to pi times times diameter d1 over 2 square. Okay, so here you know d1 equals to 10 times 10 power minus 3 meter. We can calculate v1, where v1 equals to let me calculate, equals to 5 m per second. This is the value of v1 inside. So we have one idea. We calculated v1 and by using q equals to s times v. Okay, let's go to the third. By applying Bernoulli's equation between the point 1 and 2, determine P1. I want to find P at the point 1. You know, we can apply directly P1 plus rho GH1. You know H1 equals to H2 plus rho divided by 2 V1 square equals to P2 plus rho GH2 plus rho V2 square. We calculated V1 here. Here, don't forget, we have as given, if you come back to the given, I give you here V2 equals to 4 V1. Okay, we have a relation between V1 and V2. So we go back. We have V2 equals to 4 V1. So we calculated V1 equals to 5. So V2 equals to 20 m per second. Okay, I need to calculate P1. P1. So we start, you know, H1 equals to H2. So P1 equals to P2. I said P2 equals to PO. We can say here PO plus rho over 2. We have the value of V2 equals to 20. We can say here 20 square minus rho over 2 V1 square. We have V1 equals to 5. We can say here 5 square equal 25. Okay, so P1 equals to PO 10 5 Pascal times rho of the oil equals to 800. No, we have plus divided by 2 times 400. Okay, minus 800 divided by 2 times 25. We can calculate P1. We get the value in Pascal. Okay, equals to 2.5 times 10 power 5 Pascal. This is the value at P1. At this point, we have P1. Okay, at this level where we have 1 and 2 are at the same level. Okay, we calculated for the nozzle, we calculated P1, we have P2, we calculated V1 equals to 5, and we have V2. So we have all the information for the nozzle. Now let's go to calculate the values for the mercury in the YouTube. Okay, study 2. I want to study the pressure gauge U-shaped tube. I want to find P here. The pressure gauge U-shaped tube contains mercury with density equals to 13,600 kilogram per meter cube. Okay, it allows you to measure the pressure P1 from a reading of the drop H. I talked about this point. The main idea here of the pressure gauge is to calculate P inside or Q inside by measuring the value of H is the difference between the levels of mercury at this point and at this point. Okay, let's see here. I give you Z1 minus Z3. I give you here the level from this point and this point equals to L. L equals to 1274 millimeter. The acceleration G equals to 9.8. P4, you know here, this tube is open. So here we have P atmosphere, P0 applied at this point because it's open to outside external P. By applying the fundamental relationship of the hydrostatic, because you know here we have a hydrostatic problem, it's not dynamic. Between 1 and 3, anyway, determine the pressure P3. I want to find P at the point here. Okay? You know, I need to find P. You know here, between the point 1 and the point 3, we don't have a flow of fluid. We have a static state. Okay, so we can apply between this point, you know, the fundamental relationship P2 minus P1 equal to rho GH. You know here between the point 1 and the point 2, we have a flow. We apply Bernoulli equation. Between 1 and 3, we don't have a flow. At the end, we have a static state. Okay, so we can apply P2 or P final, P below equals to P above plus rho GH. So between the point 1 and the point 3, we can apply P below equals to P above plus rho GH. You know, rho is a fluid between these 2 points. Between the point 1 and 3, we have oil. So here we have oil. H between them equals to L. We can write L. Okay, so we can calculate here. We have the value of P1, which is equal to 2.5 times 10⁵ Pascal plus rho equals to 800 kilogram per meter cube times G 9.8 times L, we have 1274 times 10 power minus 3 meter. We can calculate P3 in Pascal. Okay, equals to 2.6 times 10 power 5 Pascal. This is the value of P at this point. Okay. Part 2, likewise, by applying the fundamental relationship of hydrostatic between the point 3 and 4, you know we have a static state between them, determine H. So at the end, I need to find H. Okay, so here, let me explain how can we calculate H. Here we have to take a point at the same level with this point. We can say here the point 5, okay, 0.5. You know P3 equals to P5. Why? Because these 2 points are at the same level. Now I am talking in the case of hydrostatic fluid, a static fluid. 3 and 5 have the same level and the same liquid. So we have the same P. So we have the same P. We can take now the 0.5 and the 0.4. We can apply P5, P below equals to P4 plus rho G H. You know, rho between this point and this point, we have Hg, mercury. We can calculate P5, which is equal to P4, P0 plus rho equals to 13,600 kilogram per meter cube times 9.8 times H. I want to calculate H. Finally, we can say here P3 equals to P5. We can write P3, which is equal to 2.6 times 10⁵ Pascal, equals to PO 10⁵ Pascal plus 13,600 9.8 times H. We can find H, which is equal to 2.6 times 10⁵ Pascal minus 10⁵ Pascal divided by 13,600 times 9.8. We can find H equals to 1.2 meter. Okay, so here for a value, for any value of Q, if we have Q, for example, equals to is a given value, you can find H. Okay, now we can use this nozzle, this configuration, to find the height if we have Q. Also, we can find Q